Hello everyone. Today we are going to continue discussing our topics in DC motors. So if you remember in the last class, we started discussing the shunt and separately excited DC motors, and we derived the motor characteristic, which is the omega torque or omega T or speed torque characteristic of the DC motor. And we mentioned that in ideal case, the relation is going to be linear. However, due to the reaction of the armature current on the field current or the field circuit, the high current of load or high armature current will cause a reduction in the flux, and this reduces the flux and increase the motor speed. So this is called the armature reaction, and we discussed this in the previous class, and we will see how can we compensate that in order to cancel the armature reaction. So simply, guys, in order to cancel the armature reaction, so we need to add more components for our flux to compensate this flux magnitude in order to keep our relation linear as is. So what are the solutions? So a solution or a first solution is by adding a compensating or compensation winding. So simply, when we add extra windings on stator poles in order to produce more MMF to be in the opposite of the armature MMF, in this case, the armature reaction will be cancelled. So this is like extra component of flux coming from what's called compensation windings. So adding these compensation windings leads to cancel the armature reaction. Another way is to make what's called interpoles. So the interpoles means adding two poles at the neutral plane. So this neutral plane, the poles will produce an MMF also to oppose the armature MMF and cancel the armature reaction. What will happen if you didn't consider this armature reaction? The X of the machine is going to have like slope, so it's not going to be in the middle of the commutator, and this actually makes spark and leads to reduce the lifetime of the brushes. So the best way to avoid the armature reaction is to make interpoles or compensating windings, or both together to avoid any problem with the armature reaction. So this is a solution for the armature reaction. Now, let's go back again to our characteristics. So we are going to consider, guys, the discussion on the on the characteristic with no armature reaction. So this is going to be our linear relation for our induction motor, and this is what we're going to consider in our problems. Okay, so now, guys, some experimental notes we need to know, because this is one of the most important things in electrical machines in general, which is the parameters identification. As you could see in transformer, for instance, we identify the parameters of the transformer, like calculating the winding resistance and leakage reactance, calculating the core loss of the transformer, and the magnetization branch, the core resistance, and the magnetization reactance. So why these parameters are important to be identified, as you could see in the transformer. If you would like to evaluate the performance of this transformer, you have to know the transformer parameters. Similarly, in any other electrical machine, guys. And adding to that, for electromechanical machines like motors or generators, you may need to make speed controls or power control. And in order to control, you have to know the parameters of the motor as well, or the generator. So parameters identification is still very important task for any electromechanical device. So sometimes machine parameters like armature resistance and field resistance are not known and should be found experimentally. When you buy any motor, guys, you may ask the manufacturer to provide you with the parameters of this motor, and this should be available with the manufacturer, but sometimes it may not be accurate enough. Sometimes manufacturer may not provide you with the data if he has no accurate data. So in this case, we have to know how to identify the parameters. For instance, to find the armature resistance, we need to make a test called blocked rotor test. So blocked rotor means supply your machine, but do not allow the motor to rotate. So this test, guys, is very similar or equivalent to the transformer short circuit test. So if the rotor is blocked, this means the motor will absorb more current. So normally we make this test to stop the motor and increase the supply voltage to the motor until having the rated current. And again, don't increase the volt over that rated current, otherwise this may burn the windings of the motor itself. Okay. So when the rotor is stopped rotating, the friction losses and motor speed are zero. For sure, guys, if the motor is not rotating, so this means you have zero friction. Okay. And having zero friction means what will be the losses in our machine? Actually, the loss is going to be electrical loss. So we can consider that when the motor is blocked, when the rotor is blocked, so we can consider that this power loss will be consumed on our resistance, which is the armature resistance. So we can identify the armature resistance from this test if we can measure now the volt, the current, and the power absorbed in this test. Similarly, like what we made in the transformer experiment. Steps are as follow. So lock the rotor so that it doesn't rotate. Apply a small DC voltage at the armature terminal. Adjust the voltage till rated armature current flows in the armature. And then if you already recorded the volt and current, so you can say RA equals VA divided IA. So this is how to calculate. Or if you would measure the power, so you can get the resistance as power divided I square. So both are acceptable. This is for the armature resistance. If you would like to calculate the field resistance, so what you can do is apply a DC volt at the field terminals and measure the field current. So it's that easy without applying anything to the armature. So once you have the field current magnitude and you know the supply volt, so you can calculate the field winding resistance. Take care that when you take these results, you have to wait few seconds. Actually, it depends on the motor time constant. So if the motor is huge motor, so the time constant is going to be relatively high. If it is a small motor, so the time constant is going to be relatively small. So why you should wait? Because you have inductance in the circuit and you should wait until reaching steady state. So don't calculate or consider the calculations at transient periods. Just wait until having everything in the steady state and then make your calculations. Actually, if you are going to take these results using multimeters, so it will take, for sure, it will take few seconds. But if you are going to take these results using a data acquisition system, which is recording data, so avoid considering the transient period and just consider the steady state period. Okay, so these some important notes regarding identifying the parameters of the DC motor. And we will have experiments regarding the DC motor parameters and speed control later on in our lab. Let's start, guys, solving this question here while the armature reaction is not considered. So we mentioned that we will consider the calculations with no armature reaction. So in this example here, guys, we have a 50 horsepower, 250 volt, 1200 RPM DC shunt motor. So, you know, guys, that the first part of any problem here will provide you with the data of your machine, which are captured from the nameplate data. So all of these data are the nameplate data. Okay. So here again, the motor is 50 horsepower. So what is the 50 horsepower? So for any kind of machines, guys, it will provide you with the output power. So for the DC machine, if you find a DC machine, it will provide actually two nameplates, one nameplate for the motor and one nameplate for the generator. So you can use the same machine as a motor or as a generator. But again, we discussed before that DC generators are obsolete. We don't use it anymore. So if you find the two nameplates available on the machine, neglect the generator one and just consider the motor one. So 50 horsepower means the output power. So all of the time, guys, the power given on nameplate is the output power. So 50 horsepower here is representing P out. So we can say that P out equals 50 horsepower. 250 volt. So this is the terminal volt of our motor. So we can say V terminal equals 250 volt. 1200 RPM. So this is the given speed, which is the rated motor speed at no load. So this is called omega node, but here it's in RPM. So this is going to be in node. This is 1200 RPM. If you would like to get omega node from that, so you can say N divide pi over 30. So this will provide you with a value of your speed in radian per second. Now, he defined that the motor is shunt. So shunt means the armature winding and the field windings are connected in parallel together. So as you can see here, this is the figure of our field winding along with the rheostat or adjustable resistance. And here is the armature circuit. And he mentioned that the armature resistance is 0.06 ohm. So this is the value of RA, 0.06 ohms. And the total field winding and control resistance of 50 ohm. So the total resistance here is 50 ohm. Actually, this is at a certain condition, which is while producing no load speed of 1200 RPM. So the value of the total field resistance is 50 ohms at the operating condition when the speed is omega naught or n naught, the no load speed. There are 1200 turns per pole on the shunt field winding. So he mentioned that the field winding number of turns is 1200. Actually, we may not need to use this number if we neglect the armature reaction. So we will consider the part of this question only for the armature reaction is neglected. So what do we need here? It's very straightforward question just to allow you to know how to use the relations in case of the shunt connection machine. So we need to find the speed. So find the speed of this motor when its input current is 100 ampere. Someone may ask a question. So what is that speed now? If he still needs the speed. Actually, the speed here is the no load speed. No load means the motor is not loaded. There is no mechanical load, which means the no load current is going to be very small amount. However, he asks here to find the motor speed at 100 ampere. So this is a load current, which means for sure the calculated speed should be less or higher than, guys, less 1200 RPM or higher than 1200 RPM? Yes, correct. So it has to be less than the 1200 RPM. So it's not making sense if the motor is rotating with 1200 at no load, and when we load it to rotate with higher speed. So this doesn't make sense. So all of the time, if you load your motor, the speed is going to be reduced compared to the no load speed. So when we apply a certain load and the motor absorbs 100 ampere, we expect that the motor speed has to be less than 1200 RPM. So we need to calculate this value. Okay. So far, guys, we don't have a lot of relations for the speed. So you know that we mentioned the speed relation that we can obtain from the induced voltage relation, which is Ka phi times omega m, this is the EMF, equals V terminal minus IA RA. So this is the relation that we have and that we can use to calculate our motor speed. But in order to do that, you need to know the following. Firstly, from the right hand side, you need to have the V terminal. Actually, we have V terminal because the motor supply is mentioned here, 250 volt. You need to have the motor parameters, the armature resistance, and this is also given here in our question. You need to know a certain loading condition with the armature current, and this is also given here in part A. So we have all of this right-hand side parts of the equation, and we are still need to calculate the factor Ka phi in order to do or calculate the motor speed. So how can we get the value of Ka phi? You simply can get the value of Ka phi from another operating point. Operating point means another point on the characteristic of the machine with full data in order to provide the value of Ka phi. And we are going to assume that the flux is constant. So the Ka phi is going to be constant. And this means our resistance will not be changed for the time being in order to have a constant value of Ka phi. So in this case, we can use this operating point to calculate the motor speed at another loading condition, since the value of flux is going to be constant. So let's do our calculations now, guys, in order to get the value of Ka phi. Actually, we can get this value from the given data, which is the no load speed is 1200 RPM. So let's use the no load speed data or information we have in order to get the value of Ka phi. So starting firstly, you have now the loading current, which is 100 ampere. So the armature current can be calculated as IA equals IL minus field current. And the field current is nothing but VF divide RF, or V total divide RF, because it's shunt. So we can say 100 ampere minus 250 volt divide 50 ohms. So 250 divide 50 is going to be 5. So the armature current is going to be 95 ampere. So the field current here, guys, is only 5 ampere. Let me write these down here. So IF is 5 ampere. Now, we need to find the induced volt. So EA equals VT minus IARA. So 250 minus 95 times 0.06. So this is the value of the back EMF. The missing data, as we mentioned, is the value of KFI. How can we get this value of KFI? So we said we can get it from an operating point. So how can we do that? As you can see here, guys, since we calculated the value of the new EMF, you can say that you can compare actually between 2 points, which are the point of our operating condition and the operating condition at no load. And at no load, you can assume that the current, the armature current is 0. The armature current is 0. If the armature current is 0, so we can say that E at no load equals V terminal. Because you know that E equals V terminal minus IA times RA. So if you assume that IA at no load equals 0, so this means E no load equals V terminal. So you can compare between the two induced voltages, E no load and our EA we calculated right here. Or if you would like to get the value of KFI and substitute in the new case, it's up to you. So both are correct, because by the end, the relation between E and omega is going to be your K phi. So E equals Ka times phi times omega. And since the flux is constant, you didn't change the field resistance, so the term Ka phi is going to be constant. So you can say E1 divide E2 equals omega 1 divide omega 2, or equals N1 divide N2. Okay, so this is an easy way to get the other motor speed. So we can say now N for the second case equals E2 divide E1 times N at no load. So this is the new value of the EMF, 244.3, divide 250 at no load times the 1200 RPM at no load. So this is the new operating speed at 100 ampere. So as we mentioned, guys, 1173 RPM, it's less than the 1200 RPM. So this result makes sense to us. Part B, it's just train yourself again to do the calculations at different values, at 200 ampere and 300 ampere. So the reason is, here in part D, he will ask you to plot the torque speed characteristic using these data. Okay, so part B and C will be by the same way. So just you need to calculate the current and substitute in the relation and get the EMF, and then compare with the EMF at no load in order to calculate the new speed. So as you can see, guys, he got the new value of the current here considering the same field current, and he compared the EMF in order to get the new speed. So at 200 ampere, the speed is 1144, and at 300 ampere, the speed is 1115 RPM. So this is the way how to get the motor speed at different values. Now, in part D, plot the torque speed characteristic of this motor. In order to plot the torque speed characteristic, at every operating point, you need to know the value of your torque. How can we do that? So, you know that torque equals Ka times phi times armature current. So, if you have the value of Ka phi, you can get the torque at every current here. So let's see, guys, how can we do that? So firstly, we can get the power and compare between the electrical and mechanical power. So you know that the conventional, the converted power, EA, IA equals torque or induced torque times motor speed. So you can say that the induced torque equals EA times IA divided omega M. So you can use now the different operating points. You have 3 operating points at 100 ampere, 200 ampere, and 300 amperes. And every operating point, you have the induced volt, you have the armature current, and you have the motor speed. So simply you can get the torque of this case. So this is the relation again here, guys. Induced torque equals EA times IA divided omega M, and substitute at the different values, starting firstly with the 100 ampere. So with the 100 ampere, the induced volt was 244.3. The armature current is 95 ampere. And the motor speed, you should calculate the motor speed in radian per second. So this is the RPM, so it should be multiplied times 2 pi divided 60 or times pi divided 30, the same, in order to convert RPM to radian per second. So we got the first torque equals 190 Newton meter. Do the same for the other current values and get the different torque values. So by the end, you can plot the 3 points along with the 0 point as well, the no load point, and you will find that the relation is linear, as you can see here. So this is the torque speed characteristic, and this is again in case of the armature reaction is neglected. So this is, guys, in the textbook, example number 1, and actually another example was related to the armature reaction calculation, but we are going to neglect this in our class. If you would like to know more about the armature reaction, you can read it. Okay. So let's continue our discussion, guys, in one of the important topics of DC motors, which is speed control of DC motors. So the objective of this material, guys, or the objectives are speed control, knowing the speed control of DC motors. Series DC motor, guys, we are gonna just know a bit about series DC motor, but we'll not go more in deep, and the different characteristics of the DC motors as well. But the main goal is to know the speed control of DC motors. We will elaborate a bit in the series DC motor and the different characteristics of DC motors by the end. So let's start, guys, with the speed control. So what is the meaning of the speed control? Let me firstly draw the torque speed characteristic, or let me get a copy of the torque speed characteristic from the slides we had before, like this one, for instance. So now, guys, this is our motor characteristic. And we agree that this is called the speed at no load, which is V terminal divided Ka times phi. This is called the machine characteristic. How can we, or why do we need to move this characteristic? Actually, in order to control the motor speed, we should match two characteristics together. This is called the machine characteristic, and we have what's called load characteristic. For instance, guys, we have what's called constant load torque, or constant torque load. Constant torque load means the load that whatever the motor speed or whatever the speed of this device, the torque is going to be constant. Okay. There are some other load torques, guys, or torque loads that the torque is varying with the speed and varying linearly with the speed. We have some other loads, the torque is varying with the square of the speed. So if it is constant load torque, so let's say this is a constant load torque. Torque constant. Let me have another type of loads. This is torque load proportional to speed. Another type can be torque load is proportional to square of the speed. So here, torque load is proportional to square of the speed. Okay. So there are many functions for our torque load. So this is, the red one is called constant load torque. The black one is torque is proportional to speed, and the green one is torque is proportional to the square speed. Okay. Now, whatever the load type, it will intersect with the machine in a point. So I'm gonna delete again the characteristics of, let me delete the fan, which is torque was proportional to omega square, and delete also the constant. I will keep only this load torque to show you what will happen in order to, or how can we make speed control for our load. So now, guys, the intersection here is called operating point. So this intersection here, this is called operating point. So if I run this motor at this characteristic with this load torque, what will happen is the machine will start working until reaching to that point. And what will happen is this point is going to be the steady state operating point. So in this case, this is going to be the value of load torque, and this is going to be the value of load speed. So this is going to be our omega m in this loading condition. If I would like to reduce this speed, how can I do that? I cannot have access to control the load curve, but I have access to control the machine curve. For instance, I would like to increase the motor speed. So if you would like to increase the motor speed, we need to have operating point, for instance, like here. So I need to move the motor curve to intersect with the load speed at this point. Or if I would like to reduce the motor speed, so for instance, I would like to get this operating point. So I need to move this blue curve to intersect with the load curve at this operating point. So this is the meaning of speed control. How can we do that? Actually, it's nothing but playing with the parameters of this curve. So what are the parameters of this curve? This is actually our speed equation. So if you have a look here to the speed equation, you will find that omega m equals Vt divided Kfi minus armature resistance plus rheostat resistance divide Kfi square times torque. Torque is not a variable that, or not a parameter that we can use in order to control. So this is going to be a dependent variable. So it will vary according to our speed control. So we cannot change, we cannot say we will change torque in order to control speed. No, this is incorrect because this is a dependent variable. Okay, so omega and t will be dependent variables in the speed control. So what are the independent variables or parameters that we can use to control this curve? Actually, the controlling parameters are any other parameter in the equation. So you can find that we have the volt. We can have the armature resistance. But the armature resistance itself is not a controlled resistance. It's fixed resistance. However, we can add a series resistance with the armature resistance. So this is rheostat. So we can have a series resistance, controlled series resistance with the armature resistance in order to control these variables. Another factor is, you can see here we have Ka. Ka actually depends on the winding of the machine. So we are not going to control the variable Ka. However, we can control the variable phi. So we can end up now, guys, we have three parameters that we can control. We have V terminal, the armature volt control. We have the added resistance, so the armature resistance control by the adjustable series resistance, and the flux or field control. So these are the three techniques that we can use in order to control our motor speed. Now, guys, let's follow up what will happen to the machine characteristic and the different control techniques. So let's start with the first control technique, which is the armature voltage control. What will happen if we change the armature voltage? So what will happen to our characteristic? Here, for instance, we have a different characteristic load, which is torque load is constant. As you can see, whatever the speed, the load torque is constant. So this is our relation. In order to figure out what will happen, guys, to the machine characteristic, we need to identify the boundaries of our curve. Boundaries means the beginning and end points, for instance. So the beginning point is this point. So this is called the no load speed. So this is the point of the no load speed. This is omega naught. So omega naught depends on what? If you write the equation of omega naught, it will be V terminal divided Ka phi. It should be minus Ra divided Ka phi times I at no load, okay? But if you neglect the no load current, so this is going to be the approximate equation as we mentioned before. So we can say that the value of omega naught depends on the value of Vt divided Ka phi. So if we are going to change V terminal, for sure, the value of omega naught will be changed as well. So for instance, the direction of voltage increase is this direction, guys. So this is VT1, VT2, VT3, VT4. I can say that VT1 is greater than, VT2 is greater than, VT3 greater than, VT4. So with voltage increase, the characteristic is going to move in this direction, and the value of omega naught also will increase. So if assume this is at VT4, this is VT3, VT2, and VT1. So this is the direction of omega increase. So this is the first point. And then after that, the other point here can be obtained from the relation and the value of torque. So you know here the value of this torque, for instance. So if you substitute in your relation, you will give the other operating point. And this is a linear curve, which means 2 points are sufficient to draw this curve. So this is a way, for instance, how to draw the curves in case of voltage control. So as you can see, guys, it seems to us like these lines are parallel, but it's not exactly parallel because the rate of change is different between omega naught and omega m, because here you have kfi squared in the denominator, so the rate of change is not the same. So this means it's not exactly parallel, but it's very close to parallel, to be honest with you. Okay, so this means, guys, if you increase the volt, the intersection points with your load torque, which is the operating point, so the speed of the operating points can be increased. But do we have any kind of limitations to increase the volt? Actually, yes, we have. So we cannot increase the volt over 10% beyond the rated value. Otherwise, this may damage the insulation of the windings. So 10% overvolt is the maximum. And to be honest with you, we don't prefer to make overvolt. So reducing the volt is fine. If you would like to reduce the volt, this is okay. But increasing the volt, this is not preferred. And the maximum, again, the maximum is 10% at most. Otherwise, this may cause a problem in your motor. This may burn the insulation of your windings. Okay, so this is, guys, the way how can we make speed control using voltage. So if I ask you guys, discuss how to control the motor speed using voltage control. So firstly, you should draw the characteristic at different values and write down the relations and mention the advantages and disadvantages of this technique. So here, guys, speed control by adjusting terminal volt, VT, without changing field current. So here, if the motor is separately excited motor, so actually VT is going to be just for the armature, and the field should have another supply. But if it is shunt motor, and you are going to change V terminal, so you have to consider that changing the rheostat of the field winding in order to keep IF constant. So in speed control, guys, we don't prefer to make two types of speed control at the same time. We may use two speed controls in different intervals, but at the same time, no way. Don't use two speed control techniques at the same time. Okay, so now we have some limitation. If you don't have field control resistance or rheostat, and you use voltage control, so you cannot use it now with shunt motor. It has to be separately excited motor. So this can be considered as one of the limitations. Okay. No load speed increases, but the slope stays the same. Okay, almost the same, guys. Okay. This technique has the advantage of wide range of speed control. Can you see, guys? You can increase the volt to very low values until having zero speed here. So you can have speed control from 0 to very close to no load speed, or even increase it a bit to reach to no load speed or higher. But you have to consider that the volt is less than 110%. So the maximum over volt is 10%. Okay. So the advantage is you have wide range of speed control. Okay. And this is, by the way, one of the important advantages of speed control, to have a wide range of speed control. Okay, guys. However, it is limited by the voltage increase to maximum 10% beyond rated volt. Okay, guys. So this is, guys, the voltage control, the speed control using armature volt. Okay, so again, if I ask you what or how to control the motor speed using voltage control, so you should mention the relations, all of these relations, the characteristics, and showing what is the highest volt, what is the lowest volt in the characteristic you draw, and mention the advantages and drawbacks. Okay, so this is the complete answer of this question. The second technique is field control. So as we mentioned, guys, we can use field to control the motor speed. And even when we discuss the armature reaction effect, we mentioned that if the flux is reduced, the speed will increase. And actually, this is very clear from our relations right here. So if you write down the relations again, so our two relations, the boundary, which is the speed of no load, and then our speed at loading conditions. So these are the 2 points that we need on this curve. The first point was the no load speed and the load speed. So if you compare the no load speed, you will find that omega naught equals Vt divided Ka phi, which means with phi changing, if you increase phi, omega will be decreased. If you decrease phi, omega naught will be increased. So this is the effect, guys, here on the speed at no load. Okay. So let's say this is curve number 1, curve number 2, curve number 3. So omega node number 1 is less than omega node number 3, which means now the flux at omega node number 3 is less than the flux at omega node at this value. Okay, so the higher the omega node, the lower the flux. Okay, so in this case, V field 3 is going to be the lowest field, and this is the highest field. Okay, guys. So this is regarding the value of omega node. And regarding the other operating condition in case of constant load torque, you will have here Ka phi and here Ka phi squared. So this is going to make the slope is very like different compared to the voltage control. So in this case, guys, you will find that these curves are going to be intersect at high torque value. Okay, but we will not reach to that very high torque value. So this is called field control. So we understood now the curve, we understood the equations. So let's see what are the limitations, what are the advantages and drawbacks. Firstly, speed control by adjusting the field voltage or flux, no load speed increases and with steeper slope. As you can see, the slope is steeper compared to other or the voltage control technique. It's still wide range of speed control, so you can have wide range of speed control as well when you use field control, but should be used carefully. The speed can be so high that it can cause damage, and this is what's called field weakening. Field weakening means reduce the field to very small values and increase the speed to very high values. So this is field weakening, guys, is used to have increasing speed to up to twice of the no load speed. So what is the limitation? Actually, the limitation will be the motor bearings. So the bearing has a maximum operating speed. If you reach to that operating speeds, your bearing may be damaged. So in this case, you have some limitations for the overspeed. So most of the time, guys, we can use overspeed up to twice of the rated speed or twice of the no load speed. And the motor bearings should be designed to support that. But if the bearing is not designed to support that high speed, so you are in trouble in decreasing your flux to these values. Okay, guys. And again, this control technique or reaching to this limit is called field weakening. Field weakening in order to reach to very high speed like that. Okay, nice. So this is the field control of DC motor, of separately excited or shunt DC motor. So both of them are going to provide the same characteristic. We have here few notes. So what would happen if the field is lost? This is very good question here, guys. If the field of a separately excited motor is lost, so theoretically, if we write down the relation, you know that omega nodes equals approximately equals V terminal divided Ka times phi. So during motor operation, if you lost your flux, so theoretically, the speed is going to be infinity, which means the motor will overspeed until damaging the motor parameters, sorry, the motor bearings. And by the way, it will also absorb very high current, which is going to burn the motor windings. So this is very critical. Don't open the field circuit of the DC motor, otherwise the speed will theoretically reach to infinity. The motor will overspeed, and this will damage the mechanical parts of the motor and burn the windings of the motor. Okay, so this is very dangerous for any separately excited DC motor. Okay. The loss of field protection is needed to open the armature circuit automatically in case of loss of the field. So this is very important to have a protection. If you have field current loss, you have to have a protection to open the circuit of the armature. If you open the circuit of the armature, so the armature current is going to be zero, and zero armature current means the energy stored internally in your motor will be dissipated in the overspeeding that the motor tried to do until the motor stopped. And in this case, your motor will not absorb more power from the supply and will stop. So this is the preferred way to protect your motor against the field loss. Regarding the third technique of speed control using adjustable armature resistance, let's figure out again the boundaries of our curve. So you know that omega node equals V divided Ka phi. So there is no resistance in the function here. So this means whatever the added resistance to the armature circuit, omega node will be constant. So can you see here, guys, we have different characteristics at different armature resistance, and omega node is common. Okay. So if you add more resistances here, so this term is going to increase, which means the speed will decrease. So here you have the highest rheostat. Here you have rheostat equals 0, and rheostat is the added resistance to your armature circuit. Okay. So this is the relation between adding resistance and motor speed. So As you can see here, guys, speed control by adjusting armature resistance, not commonly used because of high losses. So if you have this resistance in your circuit, for sure you will have I square R losses during the speed control time. And speed control means it's long time operation. It's not just transient operation, which means in order to control your motor speed, you may keep the motor speed or controlling the motor speed during the complete lifetime of the motor operation, which means this resistance is inserted in the circuit all of the time. And this will increase the losses and reduce the efficiency of your motor. So this a very challenging technique because it increases the losses of your motor and reduce the efficiency of the machine or the DC motor. So this is the drawback of using these armatures. However, sometimes, guys, you may find the adding rheostat is used just in starting. Starting of the motor, it takes like few milliseconds to few, maybe few seconds in case of very huge DC motors, very high power DC motors. It may take few seconds to start up. But again, starting is just transient period. We don't care about the efficiency during starting period, but we care about the efficiency during speed control. So does it mean we do prefer to use rheostat in starting? My answer to this question is going to be no, we don't prefer it also, because it's make more sense to have one device to control your machine during starting and speed control. So we are not going to buy a device to control my machine during transient period and another device to control the machine during steady state period. So this is extra cost to the motor or the drive system that we use for our motor. So starting or speed control, we do prefer to have just one device to control both of operations during transient period and during steady state period as well. Okay, so this is the third technique that we use to control the motor speed. Is there a combination between the different control techniques? Actually, yes, we have. We have one control technique, guys, which is called constant power, constant torque control. So what is the meaning of having constant power, constant torque? Actually, it's not going to be constant power, constant torque at the same time, but it's like intervals. So we have interval for constant power and interval for constant torque. So how can we do that? So speed control from 0 to base speed is usually obtained by armature voltage control. So you can make armature voltage control in order to keep your torque constant. And keeping torque constant means the armature current is constant. Okay, guys? So we can use current control to keep current or constant current control. So constant current control means constant torque control, because you know that torque is or equals Ka phi times armature current. So if you would like to keep torque constant, so you have to keep the multiplication of flux and current constant, and we will use constant flux in order to keep the armature current constant. So in this case, we can use voltage control. So we will not control the flux here, just volt, in order to keep our torque and current constant. So this means flux is constant during this period. So first step, between 0 speed to base speed, the flux is going to be constant and only voltage controls. And after that, after reaching to the base speed, if you would like to continue increasing the motor speed, you still can do. However, the drawback is going to be your power limitation. So increasing the speed, and if the torque is going to be constant, this means the power is going to increase. So you cannot increase the power over the rated value of the machine. So the idea is, if you would like to increase the speed, this is possible. However, you have to keep your machine power constant. Constant at what value? At the rated value of the machine. So in this case, you can use here field control. So the field control, reducing the field is going to increase the motor speed, but you still have to control the motor power to keep the motor power constant. So in this case, you have to reduce your torque in order to keep your power constant. How can we do that? It's still armature current control. So you control the armature current in order to keep your power constant. Okay, guys, how can we do this? By reducing the field current. So we have now two intervals. The first interval is called constant torque control, and this can be done by controlling by voltage control technique in order to keep the armature current constant. And the second part of the speed control is to keep the power constant by controlling the current in order to reduce our torque like that. How can we do that? By using field control. So these are the two stages of this control technique, and this is called Ward-Leonard technique, Ward-Leonard technique, and or constant power, constant voltage. Constant power, constant torque control technique. So let's finish with this example here, guys. We have a variable speed drive. So variable speed drive, guys, is a power electronics circuit along with the motor used to control the motor. So this variable speed drive system uses DC motor that is supplied from a variable voltage source. So the power electronic device is providing variable voltage source. The torque and power profiles are shown in figure. So this is the torque and power profile, which is constant torque, constant power technique. The drive speed is varied from 0 to 1500 RPM. So this is the base speed of our drive system by varying the terminal volt from 0 to 500. So this is the first range of the speed control. So 0 speed is corresponding to 0 volt, and 1500 RPM is corresponding to 500 volts, with the field current maintained constant. This is extra word here. This is extra description, but just to confirm that in this stage, we use voltage control without field current control. What do we need here? Determine the motor armature current if the torque is held constant at 300 Newton meters. So this is now the torque in the first stage. It's kept constant at 300 Newton meter, and we need to find what is the armature current. Okay, so let's start, guys, with the first part. So now, the base speed, guys, or no load speed, is the 1500 RPM. And we consider at no load speed that if we neglect the losses of the machine, so we can consider that the terminal volt is the same as the induced volt. So we can calculate the Ka from here. So Ka equals the V terminal divide N times 2 pi divide 60. So this is going to be the value of Ka times 5. We have the torque, which is 300 Newton meters. So divide T divide Ka. So you will get the value of your armature current. So this is the armature current during the first interval. So this is constant current control in order to keep the torque constant. Then the speed beyond the base speed is obtained. so is obtained by field weakening. So this is the field weakening or field control. We reduce the field in order to increase the motor speed, while the armature voltage is held constant at 500. We cannot increase the volt anymore. What do we need here? Determine the torque available at the speed of 3000 RPM. So we will increase the speed to reach to twice of the no load speed. The question is, what is the current we have? Sorry, what is the torque we have at this instant here? Okay. If the armature current is held constant at the value obtained in part A, so we will keep the current as in part A. So the current here is constant. We will keep this current constant and reduce the field in order to reduce our torque. So this means, guys, we need to have constant current operation during both of intervals. The current was constant here, so this is I. It's constant during both of intervals. So at the same value of current, the speed is twice. So we have the data now. Speed became 3000. Voltage is still the same. So let's start firstly from the volt and speed. We need to get the value of KFI. Since volt is the same, so we expect that, and speed is twice, so we expect that the field will be half. So as you can see here, 3.18, here 1.56. So it's half to compared to the first flux. So now we can say that torque equals the KFI value times our constant current. So the torque is going to be half. So the torque reduced now from the first case, 300 Newton meter to 150 Newton meter. Okay, guys. So this is the new value of our torque. This is a way. Another way is you can say that the second stage is considered as constant power control, and power is E times I. So I can say torque equals EA times IA divide our omega M. So this will provide you with the value of the induced torque in the second case. Okay, so we got the same value here from this comparison. So this is, guys, an example to show you how to make the Ward-Leonard control technique or constant torque, constant power control technique of a DC motor. This is an activity or a quick assignment to you guys. Separately excited DC motor has the following nameplate: 100 horsepower, 440 volt, 2000 RPM. We need to determine the rated torque and determine the current at rated output if the efficiency of the motor is 90% at rated output. So this is going to be quick assignment. And this will be uploaded on eCampus. Okay, so our class today is Friday, so this is going to be due on Tuesday. Okay, guys, so we have very few multiple choices here. Let's read these questions before ending here. So the shunt winding has blank resistance compared to series 1. So we mentioned, guys, that the series winding resistance compared to the shunt winding resistance, what is the relation? So if the shunt winding is smaller or higher? Yes, correct. It should be higher because the series resistance is going to be very small to support the high current, and the cross-section has to be high. So the right answer should be that shunt winding has a higher resistance value compared to the series one. The DC armature losses is referring to copper losses on the armature resistance, brushes losses, all the above mentioned. Actually, the armature loss is referring to the summation of both of losses. So the right answer is all the above mentioned. The shunt DC motor needs two separate supplies for the armature and field winding, or one supply for both armature and field winding. So since this is shunt motor, so just one supply is required. The generated voltage of a DC machine depends on, so you know that the induced volt or the generated volt equals Ka times phi times omega. So the choice here we have the machine speed is omega m. The machine flux is phi. All the above mentioned, none of the above mentioned. So all of the above mentioned is correct. The DC motor torque is directly proportional to. So you know that torque relation equals Ka times phi times armature current. So the DC motor torque is directly proportional to the motor armature current, the motor field current, the motor speed. Nothing mentioned is right. So motor armature current is correct. What about motor field current? Actually, motor field current is correct as well, because phi depends on the motor field. So in this case, we have two answers. These two answers are correct. The function of the commutator in DC machine is regulate the induced voltage, rectify the induced voltage, regulate the motor speed. Nothing mentioned is correct. So we mentioned together, guys, in our classes, and we could see some videos for that. So the commutator in DC machine is converting the AC to DC, and this is the meaning of rectification. So we can say this is rectify the induced voltage. Okay, so we will stop at this point here, guys, and we can start solving this example from the next session. Thank you so much.